It is my pleasure to be here, and I think this is the second time to join for me to join. And today I will going to talk about dynamics, not statics. Although most of the speakers today seriously focus on the statics, but I try to go to deep nonlinear insight, and then give you some our recent result. And this work is basically collaboration with Shohei Saga at my institute and Stefan Colombi at IAP. And this is my plan of talk. In my talk, I will basically focus on not density, but phase space structure or large scale structure, and then try to deal with analytically such a nonlinear phenomena based on perturbation theory technique. And after briefly introducing my motivation and try to what we are going to do now, then I will briefly describe what Lagrangian perturbation theory, and then and try to describe the so-called shell crossing. And then after that, I will also go to the beyond shell crossing. But this is still preliminary. I do not have any clear or complete answer to that. But I would like to have some comment or feedback from you if you have. Then finally, I will summarize my talk. Okay, let me begin with very, trivial point in all of you. You know, dark matter is now very important, object or particles to describe the universe. Now we know that 30% of the energy contents is dominated by dark matter. And these are still unknown and mysterious components. Although these are composed of microscopic particles, but we still don't know the origin of that. But we have many observational evidence showing the presence of dark matter, including flat rotation curve or weak lensing observation, or CMB or large scale structure, especially if you look at statistics, dark matter is definitely necessary, important. And then if you talk, if you think about structure formation, then what is important, more important is the so-called nature of dark matter. If you look at, distribution function of dark matter, the velocity, when we call the velocity, width of velocity distribution function very thin, so that it can be replaced with Dirac delta function. This is what we call the cold dark matter. And this is has been proposed a long time ago as a hypothetical particle, but now it can explain many things. Since the dark matter is cold, so we do not so much care about these lengths. And then this CDM can grow up gravitationally, and this can help to help baryon to grow up after decoupling of the early universe. And then this can give you some observable baryon, not only cold dark matter, but also baryon dark distribution. And especially the cold dark matter can predict small scale structure. If you look at the result of N-Boy simulation, we see lots of very small so-called substructure. So this is the kind of prediction of called dark matter universe, and then we have some contradiction between observation and simulation. But now, thanks to the huge development of observation, now cold dark matter structure formation is now mostly consistent with observation. And another or more important point is that this, apart from the microscopic origin of dark matter, this system can be described by so-called Vlasov-Poisson system, and starting with cold initial condition. So this is a Vlasov-Poisson system coupled with, this is a collisionless Boltzmann equation coupled with Poisson equation. And so we usually this cosmological n-body simulation is mathematically equivalent if you take the number of particles to the infinite limit. And this is our basic equation for structure formation driven by gravity. And we, under this basic equation, we impose so-called cold initial condition. So this is the main ingredient of what we call dark matter. Here, this is the density field at a given position, and here you see some Dirac delta function for the velocity distribution. So meaning that at a given position, the velocity is uniquely determined by some velocity field. And at Lagrangian regime, this velocity field is tightly correlated with a linear mass density field. And then we can start any evolution of dark matter distribution. And what is an interesting point is that if you strictly assume this distribution function, and then plugging it into the Vlasov collisionless Boltzmann equation, taking zeroth order and first order moment gives you so-called single stream equations motion. That means the equation for continuity or density field, and then Euler equation without pressure for velocity field. And if you couple with Poisson equation, this system gives you the basis or foundation of perturbation theory treatment for which Francis has talked about. And then relying on the perturbative treatment of density or velocity field, then we get the precise, we can precisely predict some statistics like a correlation function of power spectrum or bispectrum. And this gives you really much accurate prediction if you look at large scale. But this treatment strictly assumes so-called single stream flow. And this single stream flow is eventually actually violated at least at small scale. And they followed by so-called shell crossing and multi-stream flow. So these are the main topic of my talk. So let me just briefly remind you what are shell crossing and multi-stream. And then to get some intuition, well, maybe a bit difficult to get into intuition, but let me consider one-dimensional cosmology. Here, this is a density profile as a function of position, and I put some small density peak at the center, and with almost zero velocity. Then the gravity can attract the mass element to the center. Then eventually, the density grow up, and then finally, you end up with some upper divergence at the center. If you, then this is a evolution of density profile, and if you look at phase space structure, you see something interesting. Yeah, velocity is almost horizontal, meaning that the velocity at a given position is multi-valued. And this is so-called shell crossing, but this shell crossing is not the end of a structure formation, or rather the formation, the beginning of a halo formation. After this shell crossing, so because of collisionless of collisionless dark matter, the mass element passing through each other, and then start to go back and forth, and then finally you end up with such a spiral pattern in phase space. And this is the formation of dark matter, realized halos. And you see this spiral pattern means that at a given position, velocity are multi-valued. So this is so you see this is a multi-stream flow. And this is just one dimension, but if you look at the three-dimensional, let's say, the result of N-body simulation, you really see such a multi-stream structure. Here, this white circle is the boundary of single stream and multi-stream flow. So it is now quoted as Schwarzbach radius, and now getting popular in especially cosmology. And inside this multi-stream flow is developing, while outside the stream is still single flow. But you see many circles, meaning that we do not ignore such a multi-stream region. So this may actually affect the so-called single stream perturbation theory treatment to predict statistics at large scale structure. So main question or my main motivation is how can we deal with shell crossing and multi-stream flow? So this can be indeed important or unique feature in of cold dark matter. So if we can even observationally detect single stream, shell crossing or multi-stream, it may provide a unique test of cold dark matter paradigm. And to do that, quantitative understanding of shell crossing and multi-stream flow is really important, especially looking at phase space distribution. And usually, and one important theoretical tool to understand shell crossing and multi-stream flow is, of course, N-body simulation or Vlasov simulation. But it will be really great if we can develop or make up any progress on the analytical understanding of shell crossing multi-stream structure. This is my main motivation. And now, thanks to the huge progress of numerical technique, now Vlasov-Poisson simulation is now made available. And it might be a very good timing to develop analytical treatment to capture the described shell crossing and multi-stream flow. And I am also hoping that such kind of study we may give some hint to innovate single stream perturbative treatment that has been talked by Francis this afternoon. And then naturally my focus of this talk is to develop some analytic technique based on perturbation theory. But we try to focus on shell crossing multi-stream flow, such a nonlinear phenomena. And to do that, we are going to use Lagrangian perturbation theory. Just give you some flash for what is Lagrangian perturbation theory. So this is an analytical approach to follow the motion of mass element, introducing so-called Lagrangian coordinate. here Q is the Lagrangian coordinate at which the mass element uniformly distributed. But soon after gravity becomes significant, its mass element, position of mass element is deviated from initial position. So to describe that, we introduce so-called displacement field vector. Basically, the Lagrangian perturbation theory deal with time evolution of displacement vector field by solving the motion of mass element coupled with Poisson equation. And assuming the displacement field is small, we can develop perturbative treatment for displacement field. And importantly, at first order, how to say, this is so-called Zel'dovich approximation. And the important point is that Zel'dovich approximation can be an exact solution if we are living in a one-dimensional world. So this is a solution, and D plus is a linear growth factor, while psi is an arbitrary function of Lagrangian position. And once you set up some initial condition, the Zel'dovich solution gives you exact motion of mass element up to shell crossing in 1D. So this is some illustrative figure showing Zel'dovich approximation or solution coincides with a simulation indicated by red line. But after shell crossing, this is no more exact, just an approximation. Then you see a big difference. Also, as I said, this is the exact solution, not only in 1D. If you think about a real world, like a three-dimensional world, then this is nothing but approximation. So we need to go to higher order to describe the motion of mass element at a deep nonlinear regime. So these are the main topic which we are now going to talk about. So first, let me focus on how to describe the shell crossing in 3D by developing higher order Lagrangian perturbation theory. So again, so this we just solve some equation motion of mass element by expanding displacement field. So this is the Lagrangian perturbation theory. So in order to do that, we have to derive the motion of evolution equation from displacement field. Since displacement field is the three-dimensional vector, we can naturally decompose into the so-called gradient or curl mode, or let's say longitudinal or transverse mode. So this is a divergence part. Then this is a rotational component. And this is the basic equation for displacement field. And you see at the right-hand side, there are source terms, so which appears from through the nonlinear interaction by gravity. And in test, so this looks very complicated. So what we can do is to do perturbatively solve these equations. But interesting point is maybe that if you just consider the one-dimensional world, all nonlinear terms can disappear because of some symmetric reason. Here, epsilon is a Leibniz symbol, so we not have any antisymmetric part in one-dimensional case. So what you get is just a linear equation for displacement field. And assuming transverse mode is ignored, so the solution is nothing but linear growth, linear evolution equation. So this is on the this is what Zel'dovich solution tell you. But in 3D case, we can't ignore nonlinear term, so we have to perturbatively treat it. But more important or more difficulty might be that even if you can solve these two equations perturbatively, you must reconstruct the displacement field itself out of these two solutions. This is also non-trivial task. So in order to do it in a tractable manner and analytical manner, we need to assume some initial controlled initial setup. Here we consider some isolated system composed of single density peak at the center, and where we put initial displacement like given by a single mode sine wave, 3 sine wave. But we allow to introduce some free parameter for the amplitude of sine wave, with which we can choose the evolution or speed of evolution. The cell crossing can be different by varying these parameters. And then with this setup, we can do some tractable analytical calculation. And my collaborator, Shohei Saga, actually did a very tremendous job to develop the solution up to 10th order. To give some flavor, I just give you the analytical expression for the displacement field, just restricting only the x component. And this is the second order, and the third order, the fourth order. A little bit gets long, expression gets longer, but still it's compact. And this is fifth order. But if you go to more than sixth order, it can be in trouble. This is sixth order. And this is seventh order. Now, probably it's very hard to see what is lithium. And eighth order. And then finally, you end up with 10th order. I can't even see. Anyway, this is what he got. But with only with that expression, we still don't understand what is going on. So in order to understand what is going on, we will try to make a comparison with numerical simulation. So that is a Vlasov-Poisson simulation. This has been already introduced by Mark Nerling yesterday, but just give you some flash. So what we use is a so-called Cordice code, in which the phase space is represented by a collection of so-called simplex. And what is nice is that this code gives you the exact projection of phase space C in 6D onto the density field in 3D. And with which we can accurately compute the force or potential using a Poisson solver. And then an element is, or each simplex is adaptively defined, and we can go to really very deep nonlinear regime. So here is just a demonstration in what's going on in 2D case. And in phase space, this is 4D. So we try to make a comparison with Lagrangian perturbation theory in 3D. And this is the part of the result. So since we are now looking at 3D case, so that the phase space is 6E, it is very hard to see or imagine. Then we just stick to just one axis, focusing on x-axis, and then try to see the one-dimensional, two-dimensional phase space structure. So this is x and bx, while y or z axis is setting to 0. And periodic boundary at here and here. And black dotted line are the result from Vlasov simulation. While faint gray dotted line are the prediction based on Lagrangian, Zel'dovich approximation. So this, we chose the setup of the amplitude of the density peak is something like this, so that shell crossing is close to one-dimensional case. But we still see some difference because we are now looking at 3D 3D structure. So we need to take into account higher order Lagrangian perturbation. And we not only quasi-1D case, we also consider the other cases. So upper one is the case where when shell crossing happen along not only x direction but also y direction. And left one is a very peculiar or rare case that those shell crossing can happen simultaneously along x1 z-axis. And you see the structure is really different, especially this one. But these two looks similar. And the question is how higher order Lagrangian perturbation can catch up the simulation result. So here I add fifth order. Now this case is almost perfect, but for quasi-2D initial condition, it still have some discrepancy. And also in 3D collapse, we have a substantial discrepancy.
Do you have a grid viscosity in this?
Grid viscosity.
It has to be numerical smooth, right?
Yeah, but we try several grid resolution size, and then at the level of comparison, it's almost converged. And then, so fifth order is not sufficient to describe these two cases. So Shohei Saga give me a 10th order, and what is this? The red one is a 10th order. And now for quasi-2D initial condition, it's almost perfect. Agreement is perfect. But still, in 3D collapse, we still have some discrepancy. But now he has the full expression for up to 10th order, with which we can keep track of this, how the prediction can converge to something. And then he found some nice fitting form for the series of convergence. For this can be applied to each Lagrangian position. And this is a function of order of perturbation. And once we hit the prediction up to 10th order, so you can extrapolate to infinite order to get some extrapolatory result. And this is it. The cyan line are the prediction based on extrapolation. Now, remarkably, the extrapolation works very well, and to match the simulation almost perfectly well. And using making full use of such extrapolation technique, now we can investigate the all parameter range to see the generic structure of shell crossing. So here what I I'm plotting here is the amplitude of maximum velocity and its Lagrangian position in the bottom panel. And they are plotted as a function of parameter space. Now we are looking at the late stage of structure, so that the ratio is only the important parameters. Yep.
One quick question, the slide before, why is it that the velocity diverges?
That's an important question. Yeah. Now you see. So this is the case when the shell crossing happens simultaneously. So that how to say mass accumulation getting very fast. So there is a very strong attractive force near the center. Then the particle near the center can accelerate rapidly. So you see some blow-up structure, spiky structure. Okay. And you see some color gradations. This is just indicates the amplitude of maximum or Lagrangian position. And you see color gradually changes, meaning that structure of shell crossing is almost not so much drastically changed, and rather it's close to the one-dimensional case, what we are looking at like this. But so exception here is that the light upper part. Here you see red color only at the edge of the right upper part. This is a case when the shell crossings simultaneously happen along XYZ. This is only the case. So in other words, just except for this part, so most of the shell crossing structure is very close to. So this is a very peculiar feature you see. You have some spiky structure, but except for that, almost shell crossing structure is quite similar to what we see in one-dimensional case. So this may be very promising in the sense that we can, somehow describe shell crossing structure and beyond shell crossing using some one-dimensional treatment. So this point motivates us to develop some technique to go beyond shell crossing. Here we just stick to one-dimensional case, and then try to describe the dynamics after shell crossing. So what is difficulty in to deal with post-collapse dynamics is that phase-space structure has some multi-value at some given position. But in 1D case, it's a bit analytically tractable. The idea is that we just extrapolate. We use some single stream treatment to extrapolate this region, and then compute some back reaction to the single stream flow. In 1D case, this is so we use a Zel'dovich solution as a background flow, and then compute the back reaction to the Zel'dovich flow. But to do that, we expand near the shell crossing region in polynomial form of Lagrangian position, and then compute the force analytically or more rigorously. Once you get some force, exception force, the rest is to just integrate the force over the time from shell crossing to at a given time. This gives you the back reaction to the velocity. And further integrating the velocity give you, over the time, give you the back reactions of position. In this way, we can do, get some analytical expression described as a polynomial form of the Lagrangian position up to the 7th order. So this is the demonstration on how our post-collapse treatment can describe the motion of mass element after shell crossing. The red one is a simulation, and blue one is an approximation based on post-collapse perturbation theory. And of course, this is just an approximation, and then it soon after might be violated, but it still can capture the structure of shell crossing or post-collapse phase space. And especially density profile is really very nice. You can see very quite nice agreement. And based on this, we now try to apply it to the 3D case. In this case, we use 10th order Lagrangian perturbation theory developed by Shohei, and we extrapolate it to use a background single flow, and then just ignoring other interaction along other direction. We compute we made a prediction. So this is blue line, and the red one are the result based on Vlasov simulation. The first part, just after the shell crossing, it looks fine, but sooner or later we see the significant deviation. This is very different from what we see in 1D case. So this is because in this treatment we ignore the interaction between x, y, and z axis, so that we miss something important of a multi-dimensional effect. So in this way, this is still preliminary, and in order to catch up the post-collapse phase, we need to deal with really three-dimensional treatment for the post-collapse perturbation theory. This is still work, so we need still progress. But the investigation of such a post-collapse phase is really interesting. Here, this is the result taken from Stefan. This is a real-time evolution of phase space. So you see this is a different initial condition. And the development multi-stream flow is really still different, although we already have long-term evolution. And also, if you look at the structure of density profile, not profile, density structure in 3D, you see rather different structure. So this structure may give you also impact on the not only the internal structure, but also external structure coupled with some tidal field. So I think still we have many things to do, but they are very important and interesting. And okay, I'm now summary. So in this talk, I basically describe the higher order perturbation theory, and in some controlled initial condition, we developed the Lagrangian perturbation up to 10th order, with which we have for the first time made a detailed comparison with Vlasov-Poisson simulation, and we got some very nice result, and then find some generic convergence structure. But we still need to do a lot of things to describe the dynamics beyond shell crossing. But so this has to be. I hope I will present the progress near future. Okay, that's all. Thank you very much.